Welcome to Lessons from the Clipboard, where today we're talking about rational versus irrational numbers. This is Minnesota Benchmark 8.3.5.1, which says classify real numbers as rational or irrational, and know that when a square root of a positive integer is not an integer, then it is irrational. And so we're going to break this down a little bit and make sure we can understand these two things. And we're actually going to be starting with square roots. But before we do that, we need to make sure we define what does it mean to be a rational versus an irrational number. So a rational number is any number that can be expressed as a fraction, p over q, with p and q contained in the integers and q not equal to 0. All right, so back up a little bit. We got this funny looking q. This q actually means the set of all rational numbers. And then we have this z here, which means the set of all integers. And so rational numbers are defined in terms of integers. So integers, if you recall, are the numbers 0, 1, 2, 3, 4, and going on to infinity, and then going the opposite way, -1, -2, -3, and going on to infinity in the negative direction. And so if we can make this one an integer and this one an integer, then we can make it into a fraction. Now, q can be 1, and that's fine. So if you have 6 over 1 or 6, which we just leave at 6, we don't put it at 6 over 1, we just leave it at 6, then that is a rational number, okay? So we can put anything over 1, and that does not change the value. It's like dividing by 1. But we can't have q be 0. If q is 0, okay, so your p is some number, a non-zero number, and q is 0, that's undefined. And if you have 0 divided by 0, that is indeterminate. We don't want either of those situations because math gets messed up, is a quick way to say it. Okay, and then we define irrational numbers, and again, you have this q. It looks almost the same, but you got this up here, and this little, it looks like a prime or something like that, but actually that is basically saying the opposite of the set of rational numbers. So I just put, it's not rational. Because you have rational numbers, we express them as a fraction, where these are nice numbers, not like pi or e or gravity or something like that, okay? So first thing we're going to do is we're going to take and kind of talk about this second part. Square roots of positive integers, not an integer. Okay, so before we even do that, we should make sure, do we understand exponents, okay? So if you have x, which we're going to call this is a base number, and you have a taken to some power, okay, and this is your power. I'm just gonna. Then this is equal to x multiplied by itself and you're doing it n times. So if you look at an example of this is 3 to the 4th power, that means that's 3 times 3 times 3 times 3. Okay, if you look at 7 squared, we say that is 7 times 7. Okay, and well, you say, well, that's 49. Yes, it is. That is not incorrect. Okay. But one thing we want to do is sometimes we want to take the roots. Okay, and so roots is very similar. And roots undo exponents. Now, that may not be a very mathy definition, but it's what I would say is a working definition, something that we can try to understand. And so you have, sometimes you'll have, it'll look like this. So we'll do, and then we're going to put, we'll put 3 to the 4th. We'll make it a little bit easier. So if you look at something like this, this 4 here is called the index. Okay, and this is going a little bit deeper than we need to, but really what this is saying is that if we have something to the 4th power, what comes out is our base number right here. Our base number, and so this ends up being 3. Okay. So what we really want to look at are square roots. Okay, so square roots have an index of 2. Okay, and so we can take, for example, the square root of 5 squared, and that is 5. Okay, so it undoes a square. Okay, so if you took the square root of, let's just say x squared, then we can say well, we have to actually say that's the absolute value of x, which just means that what is coming out is a positive number. Okay, and that is another conversation I don't want to get into right now. But we're going to look at square roots because sometimes square roots are rational numbers. They come out really nice, okay? And if we go back to our benchmark, it says no, when a square root of a positive integer is not an integer, then it is irrational. Okay, so in order to do that, we need something called looking at perfect squares. And so you have 1 squared equals 1. So 1 is the perfect square. And you have 2 squared equals 2 times 2, which is 4. So 4 is the perfect square. And we can keep on going. 3 squared equals 3 times 3. And you start to get the gist of it, is 9. Okay, and so then we can keep going. 4 times 4. And what we get is the perfect squares are 1, 4, 9, 16, 25, 36, 6 times 6, 49. Oh, we saw that right here. So 49 is a perfect square. 64, 81, 100. We keep on going here. We get 121, 144. It's 12 times 12, 169, 196, 225. And you can keep on going because we don't run out of square roots because we're not running out of numbers. Okay, so if we can take the square root of any of these numbers, it gets us back to our base number. So looking at one of these, let's look at square root of 144 equals, well, that equals 12. And so thinking about this, 12 is a rational number, so therefore square root of 144 is a rational number. Thus, since 144 is a perfect square, oh my goodness. Perfect. I should try that again. Got ahead of myself a little bit. Since 144 is a perfect square, it is rational. Okay. So since 144 is a perfect square, it is rational. All right, so we're going to stick with square roots real quick and finish up this second part, and then we'll come back to that first part. So let's look at examples. Which of the following are rational? Square root of 60, square root of 196, square root of 44, let's do square root of 1, and square root of 2.3. Okay. Now let's do one more. Let's do square root of 1.44, just to throw something a little more challenging in there. So square root of 60 is, so 60 is not a perfect square. So perfect squares and 60 is not a perfect square. I see it. No, I don't see it over there. 196, yes. So that means this is contained in the rational numbers. 44, So this is contained in the irrational numbers. Make sure contained in the irrational numbers. Okay, square root of 1 is 1, so it's contained in the rational numbers. 2.3, contained in the irrational numbers. So I got that little prime up there. So if you said that this is irrational, you did a little differently and made a list of the rational and irrational, that'd be fine. All right, so this one is the one that's going to give us a little bit of issue. But if we think about this, 1 2/10 times 1 2/10 is 1 44/100. So that comes out real nice because, so 1 2/10 is actually a perfect square. Okay, now this is going a little above and beyond because positive integer, the square root is not a positive integer. It is not an integer at all, but this one is actually contained in the rational set of numbers. I'm going to put a little line here, just divide that out. Okay, so that should clear up anything that is dealing with square roots, okay? Other examples of irrational numbers. Examples, pi over 3, okay? And by the way, pi is approximately equal to 3.14159, and it goes on, okay? You get this e, which is, if we say equal to 2.718281828, oh, look, it repeats. Oh, and then it doesn't, okay? And it goes on from there. So I said it's equal because if I said it's approximately, the approximation, if I terminate this, is now rational numbers, okay? So let's look at rational numbers. And I could have just put that funny looking Q like I did up here. Okay, so rational numbers, okay, either, so there's one of two options. One, terminate. Okay, so some examples of that would be like 6, like we talked about. 2.415. Negative 65.3. Okay, whatever. Those terminate. They stop. The rest of the numbers are 0. Don't worry about it. Okay. Our fractions. Doesn't matter how ugly they are, like 1/3, 7 over 912, negative 65 over 4. Okay. Oh, by the way, up here, terminate, we could have put less square root of 196. That does terminate, okay? But I think we kind of covered it up here. And then, obviously, irrational numbers, you could put square root of 2. Okay, go look up square root of 2 and the Pythagoreans, and you'll find an interesting story. 3, example, is non-terminating. But repeating. Okay, so hold on a second. We got some others we can put up here because there's also numbers like 1.5349 ... What's the next number? Well, you got 1 in 10 chance of getting it, okay? But then you also have some that even have a pattern. Negative 6.123, 223, 2223, 2222. Okay, so it looks like there's actually a pattern, but this is not what I would say is a repeating pattern. Versus non-terminating but repeating, 4.919191 ... When you see the ... it means it's continuing, but look, was there a pattern going on? We could write this as 4 91/100 repeating. So this one is repeating. So that repeating bar, that works really well. Okay, and then 5/9 we know is 0.5 repeating, okay? And so if I look, I should have done this backwards, but like 0.5 repeating is, we can write as 5/9. This one we can write as a fraction, which is our fractions, which is 4 and 91 over 99. So that is how you can write these, and so now they are fractions, okay? So we talked about when square roots of positive integers are not integers, then they are irrational. And we had obviously a little bit of a counterexample, but the standard is really looking at what about, this wasn't an integer to begin with, so I guess it's not a counterexample, my bad. So here, these four were integers. This one's perfect square, this one's perfect square, so therefore these two are rational. These two are not perfect squares, so they're not rational, or they are irrational is how we're calling them. And then we looked at classifying real numbers as rational or irrational. So we want to make sure we distinguish between the two. And obviously, when we're looking at this, if it terminates, it is going to be rational. If we can write it as a fraction, and you look up here, and the numerator and denominators are both rational numbers, then it's going to be rational. So we could continue to look and say, well, what about the sum? If you have a sum of rational numbers, the sum of two rational numbers are going to continue to be rational. I could put those two together, and it's going to continue to be a rational number. Where the sum of two irrational numbers are going to be still irrational. Even if you add something to an irrational number, okay, unless you're obviously taking e minus e, then that gives you 0. So if you're doing something like that, then maybe it would be something different. But otherwise, unless you're subtracting kind of the same thing as what it is. But when you look at product, you can, when you look at square roots, like square root of 2 times square root of 2, that can give you a rational number. So square root of 2 times square root of 2 gives you a rational number. However, pi squared gives you still an irrational number. So you have an example and a non-example. So sometimes when you multiply irrational numbers together, sometimes, like with square roots, you will end up getting rational numbers back. But otherwise, aside from that, product will keep either irrational or rational. So rational times rational number is not going to change the if it's rational or irrational. Okay, so that is rational versus irrational numbers, lessons from the clipboard.